Alright, let's continue. Final problem from our list of examples. How did we do this one?
Use the quotient.
What rule are you thinking when you want to do this? What's the rule that you're trying to apply here?
The quotient.
Like the general rule.
V prime. Is that what you're saying?
But you have an ln here.
The way I did it, I did that after. So first, but I don't know if that's correct.
Yeah, that's why I want to tell you. What rules were you thinking of applying? So I wanted to know your strategy.
So I do derivative of that first over that. So because.
Right. So that means, why did you do that? There must be a rule that says you could do that.
Chain rule.
Yeah? Yeah, but what is the full rule?
Ln of x.
No.
Ln of u.
Ln of u is u prime over u. So that's the rule you're thinking of applying, right? So you're going to be like, okay, I'm going to find the derivative of this, and then I'm going to divide it by that. Now, of course, approaching it that way is going to be extremely messy, as you probably found out later. So there's a better way than to just jump to that rule. You want to do this another way. This is what everyone did? Like, you just like straight in, like, yeah, I'm just...
Could you use the product rule? I don't know. No.
Yeah?
Could you do like 1 over what's inside there and multiplication of everything?
Well, that's going to be the same thing. I mean, and this is the same as 1 over that times that. Yeah.
You can expand it because of log rules.
You can expand it with log rules. Now remember, one of the things I mentioned last time is that you always want to try to simplify with algebra before calculus. You want to kind of apply your algebra rules before your calculus rules. Now I know you're all in calc mode and you're all super focused on calculus, but you always need to take a step back and see, do I really need to go through all that? I mean, that's going to be messy with me applying that rule right over. Like the derivative of this thing over that thing, come on, and then maybe I have to simplify that afterwards. That's kind of going to be annoying. What I would actually do here is apply the log rules first. And you're going to see after doing that how easy this is to apply the log rules first. Now, note, if I apply the log rules, what does that say this is? This. Applying log rules to like the breakdown.
8 ln 2x plus 1 minus 5 ln of x squared plus 1.
Now, wouldn't you rather do calculus with this than that? Right? Now, at this point, finding the derivative is going to be pretty easy. Your y prime is going to just be, well, it's a constant factor rule, so you're just going to leave that constant alone. Differentiate this, u prime over u. Move on to the next part. Constant factor rule says leave the 5 alone. Derivative of this, u prime over u. So it's just 16 over 2x plus 1 minus 10x over x squared plus 1. And bet you that was faster than whatever you tried to do by applying this rule. It's not that this is going to be wrong, it's that it's not going to be very efficient to apply that. So once you see a log, you should be aware that there are rules that can make this simpler. So there are going to be times where I'm going to ask you to differentiate something complicated, like I'm going to, like, the derivative of ln of the cube root of x squared e to the x cubed over the square root of x, or something random like that. And if you were to approach that directly, using the chain rule and the quotient rule and all that stuff, it's going to be a mess. You're going to take forever. Whereas if you just apply the log rules, that's pretty easy to actually deal with. that should just be, I mean, with the log rules here, this would be like the derivative of 1/3, because you bring down the third power, of 2 ln x plus x cubed minus 1/2 ln x, right? And that's super easy to do with each of these. So that's where these little rules come from. So yes, I gave you a lot of powerful rules to deal with derivatives, but that's the thing. They are often very powerful in the sense that it's overkill sometimes. So you tend to want to use your algebra to simplify things whenever possible before actually applying the calculus rules. And it can make your life a lot easier. The log in particular is one of those things. Once you see ln somewhere, it automatically means you can make the calculus easier as long as you can apply the log rules. And in fact, something I'm going to teach you, hopefully we'll get to that by the end of today, is going to be a situation where when you have something complicated, you can put the ln in the problem to simplify it and get to the answer that way. So sometimes even when the log isn't present, you can actually throw him in there just to make your life easier at the end of the day. So if he starts out being there, that's even better. You can just apply the log rules first. So yeah, problem 19, it's easier than just jumping straight into the derivative log rule. Apply the algebra log rules first. Kind of always want to go with the simplest thing you can get away with. Try to get away with that first, then you kind of scale up if you have to. So we now know how to take a bunch of derivatives. I want us to do now finding derivatives in a different context. So we're moving on to the next section. This is 3.5, I believe. And here we're going to talk about implicit differentiation, as it's called. And at the same time, we'll cover something called, as this is foreshadowing, log differentiation. So that's kind of when you don't really have a logarithm there, but you throw one in there to make your life easier. So that's what we're going to do. Now this is actually going to be a very important topic because now I'm going to explain to you what the word implicit means, and then we're going to see why this is actually an important kind of differentiation that we need to worry about. So that is, there are two ways
It's like you won't try.
to express function formulas. Okay, so how do we normally represent functions? Well, one way is called the explicit way. Explicit. Right? Now, what does it mean when a function is defined explicitly? This means it looks like y equals f of x. Kind of how you always thought about functions. Y equals some function of x. So f of x is some formula that has x's in it, and the y is isolated on one side. So here you would say y is defined explicitly. So this is like example, y equals x squared, or y equals x plus 1 over x plus 2, or y equals the square root of 1 minus e to the x, right? All of these situations is your function being defined explicitly. Now in all these 19 examples that I gave you before, I gave you functions where y was defined explicitly. Y equals this, y equals that, y equals that, y equals that. These were all just an explicit way to define your function. And of course, how would you find derivatives in that situation? Well, exactly how we were finding them the whole time, right? So you just apply the rules to the right side that you know about, right? And that's one situation. But there's another way. There's an implicit way to define a function, right? Now, implicit means the definition of the function is implied, but you might not necessarily know what it is. And this is when you have something like, it's a formula, but it has x's and y's in it kind of mixed together, and maybe a constant on the other side, right? So for example, like x squared y plus 2x equals 3 ln y, right? So in theory, you're like, okay, so you're thinking of the y as some function. You know that this is some function of x, but you don't really know what that function is because your y isn't isolated on one side. And sometimes you can actually solve for the y, right? So, or like xy equals 1, or like the equation of a circle is a function, a way to define a function implicitly. So technically here you know that your y is either the plus or minus the square root of 1 minus x squared, right? But it's not explicitly out in the open that that's what your y is, right? So this is an implicit way to define your function. And it turns out, unfortunately, a lot of times in real life when you're trying to apply math to real world situations and you're figuring out formulas that connect different things that you want to study, the formula is not going to drop in your lap in this form. Oftentimes it's going to drop in your lap in this form. Right, you're collecting statistics and you're collecting measurements and you're doing all these you're sciencing the hell out of things, right? And once you say, okay, I'm measuring like volume and pressure with these two things, and you're like, what is the connection between these things? You try to connect them. A lot of times the connection comes to you in this form. But at the same time, you still want to be able to do calculus. You still want to be able to talk about rates of change. How fast is this thing changing when that's changing, right? But you're not in the nice little neat package situation. We still want to be able to find derivatives in this situation when our x's and y's are kind of jumbled together. And we may or may not be able to separate them. Like we can separate them in this case, but like that case, you can't really solve for y here. So that's what implicit differentiation is about. Differentiating in this situation, right? What we've been doing the whole time is explicit differentiation. Now we want to talk about implicit differentiation. So, implicit differentiation. This is differentiating in the implicit case. And I'm going to, eventually by going through examples, I'm going to kind of show you why this would be an important thing to be able to do. But in the moment, how do we actually do this? And it turns out, the answer is surprisingly simple. It's just apply the chain rule. Right? To be able to find a derivative in this situation, it's a matter of applying the chain rule. And so let me show you some examples of what I actually mean. So, illustrative examples. So, I want you to find the following derivatives. Now notice the thing that makes the implicit case somewhat scary in the beginning is that you don't really know what the y is. So now I'm going to tell you how would you find a derivative if you don't know what the main function is. So example, how would you find the derivative of f of x? Right? I'm not telling you what f of x is. Or how would you find the derivative of x times f of x? Or how would you find the derivative of f of x squared? Or how would you find the derivative of, say, x squared f of x squared? How would you find the derivative? I mean, at this point, after getting through all of these, you're going to sort of see what I'm talking about, of ln of f of x. So let's actually go through these. We're going to find the derivatives of all these situations where you don't know what the f is, right? So I'm going to do the first one. It's, it's the most complicated one there is, right? So how would I find the derivative with respect to x of f of x? Well, that's f prime. So whatever the derivative is just the derivative. Like, what am I going to tell you? I don't know any more information to give you. All right, go. You do these. If you have to differentiate this, how would you do it? Based on what we've learned so far, you have x times f of x. So your f of x is just some random function.
Power rule? I don't know.
What does the power rule say? What is the power rule?
Like f of x and g of x.
Right, product rule. You mean.
Oh, the product rule.
Yeah, product rule. So you think of these as two functions, like that's like an f and that's a g, right? Okay. Knowing that, how would you continue? So what would that say the answer is?
F prime g of, or yeah, g of x.
Times g, which is just x.
Yeah.
And then?
Yeah, g prime has, so.
What's g prime?
1.
Yeah,
Times the f. Yeah, that's exactly how you find it. Like, you can't say anything more than that. But whatever the derivative is, this is going to be a formula that allows me to get it, right? What about this one? This is kind of cramped. Let me just write that below. So the derivative of this one, you could just, differentiate the x, leave the f, plus leave the x, differentiate the f, right? You apply the product rule. Right? Now, at the moment here, you're not seeing where the chain rule is coming in, but the next example should show you how the chain rule is coming in. How would you do that one?
Would it be 2 f of x? 2 times f of x? Or times f prime?
Times f prime, right? That's where the chain is coming in. So now remember what the chain rule says. Now, if you had to differentiate x squared, we know how to differentiate that. That's 2x. But we don't have an x squared. We have something plugged in the place of the x, right? Namely an f of x. How do you deal with when one function is plugged inside another function? Chain rule. So what you're going to do is you're going to differentiate the outer function, which we know we can do by the power rule, bring the power down, subtract 1 from the power, leave the inside alone. So that's your 2 times f of x. But then what do you need to do? You need to multiply by the derivative of the inside. So the derivative of this is going to be 2 f of x times f prime of x. That's what that derivative would actually look like, right? By applying the chain rule. What about this one?
Product rule.
Product rule. Okay, so what we're going to do?
The derivative of
Differentiate this one, leave that one alone. Plus, and you leave the first one alone, and you differentiate this, which is
2f of x times the derivative of f.
2f times f prime. And why the times the f prime? This comes in because of the chain rule. So here, this comes in because of the chain rule. We're using the chain rule to differentiate this part. We need chain rule. So I can think of this as, say, 2x f of x squared plus 2x squared f of x times f prime of x. How do you do this one?
F prime x divided by fx.
Right, and
times-
again, that's f prime of x over f of x.
Times f prime x. Would you have to-
No, you already did the f prime x, right? So technically it's 1 over f times f prime, that would be the chain rule, but now it's just f prime over f, right? Derivative of ln of u is u prime over u. So notice what we've been doing here is that if I don't know what f is, I still kind of deal with it using the chain rule. I just know that there's some inside function, I don't know what it is, but I'm just going to differentiate the inside function and multiply by the other one. So here's another way I want you to look at this. So now we're going to look at the same examples, but I'm going to just change the notation slightly. So instead of writing f of x, I'm going to write y. Over here, I'm going to write the derivative with respect to x of x times y. Over here, I'm going to find what is the derivative with respect to x of y squared. Over here, derivative with respect to x of x squared y squared. Over here, what is the derivative with respect to x of ln of y? So now, one thing I want you to notice is once you see it, you're still trying to apply your derivative rules as normal. You see two things multiplying, you're applying the product rule. You see something raised to a power, you're still applying the chain rule, all of that. But the chain rule is what's going to be running through all of them. At some point when you're differentiating the part with the function, you have to multiply by the derivative of the function because of the chain rule. Now, if I just call the function y instead of f of x, what's going to happen? Well, this would be prime. What would this look like? The derivative of x times y.
1 times y plus x y.
What would this derivative look like? Literally exactly the same thing. I'm just literally changing what I'm calling the function. If I had to differentiate an x squared times a y squared, what is that going to look like?
2 would still just be 2x and then y times y squared. Plus 2x squared y y prime.
You still go through the product rule. So you differentiate the x squared, leave the y squared, plus you leave the x squared and you differentiate the y squared. When you're differentiating y squared though, you have to understand y is an inside function. I just don't know what it is. So I differentiate around it to y, that's this part here, but then I multiply by the y prime because it's really an inside function. I just don't know what the inside function is. What would this derivative look like? Y prime over y. Again, I know the derivative of ln x is 1 over x, but if I replace the x with something else, the chain rule takes effect, so it becomes u prime over u. And in this case, the y is like the u, so it's u prime over u. So if I see ln of y and I want to differentiate it with respect to x, it's going to look like y prime over y. So this, I'm basically teaching you how would you go about finding a derivative if you have your x's and y's mixed up. And this is the trick. You're just going to think of your y as some inside function, right? So whenever you're differentiating the part with the y, you just automatically multiply by a y prime. Right? So you go through, you apply your derivative rules as normal, but every time you deal with a y situation, just multiply by y prime, because the chain rule is what's taking effect. Okay. Now let's actually put this all together. Examples. Suppose we had find y prime, which is dy dx specifically. Right, so I'm identifying x as the independent variable, that's your input. And I told you that this is the formula, xy equals 1. Right? And I want to find y prime, but my x and my y are multiplied by each other. My y isn't isolated. Now, with implicit differentiation, what would this look like? But with implicit differentiation, since my y isn't isolated, what I would do is I would differentiate both sides. So, differentiate derivative of the left side, what would that look like? Derivative of x times y.
1 times y plus x y prime.
Alright, you apply the product rule because we have a product of functions. When I get to the y, what is its derivative? Well, it's whatever y prime is. So I'm applying the chain rule here, multiply by derivative of the inside. Derivative of 1? 0. Now suppose I actually want to solve for y prime, that's the whole point. Now this is just an equation where y prime happens to be one of the things in my equation. And so at this point, I can just use algebra to solve for the y prime.
So then is that going to be the inside function? Or
It's the y prime is the derivative of the inside function. But what would that look like here? If I want to solve for y prime? Algebra. Yeah.
A negative y over x.
Right. You subtract y from both sides, and then you can divide by x. Now, how do I know I wasn't dividing by 0 here? Can x be 0? Yeah?
No, because that says it equals 1, and if x
Right.
is equal.
So I know x is not 0 because of the original equation. Right? If x was 0, that would be 0. So I'm not worried about division by 0, and so that's y prime. This is the answer. And another thing that some people are squeamish about when they first see this is the fact that there's a y in the answer. Right? So I tell you, what is the derivative of this function? Well, it's y over minus y over x. Right? Y is a part of your answer. So your y prime is minus y over x. Now I want you to compare this to, so let's say I gave you that and I asked you, find y prime, but you didn't even know about implicit differentiation existing. How could you use what we did before to find y prime? What would you have done?
can you divide both sides by x?
Right? Your y is just 1 over x, right? I know x is not 0, I could do that. Now I'm in the explicit case. And how would I find the y prime now? So y is 1 over x. How do I find y prime? Yeah?
You could do like x to the negative 1 and do the power rule.
Right, which gives us
Negative 1x and then 1 minus.
minus 2, or minus 1 over x squared. Okay. So, turns out that that's the answer. Okay, so the first thing we need to deal with, are these both correct? Because the answers actually look pretty different. Is this wrong? Is it, like, how do you reconcile these two? Because I did it both ways. I used implicit differentiation, that's my answer. I use explicit differentiation, that's my answer. Are these equivalent? Is minus y over x a valid answer? Like, does that even make sense?
No.
So yeah, like the chain rule is wrong. Like that's not a valid way to do something. No, we prove that this should be okay. It should be okay doing it this way. What's the difference between these two answers? Yeah.
Doesn't it just mean that like that negative y is really just negative 1, like actually? Or no?
Well, the negative
Oh,
y
no,
is,
never mind, because the x squared too, never mind.
yeah. But you're kind of going down the right road, actually.
Yeah.
Like, what's the difference between these two answers? This one doesn't have a y in it, right? So that's the first obvious difference. Could we get rid of the y from this situation? Right? Are both valid? So if I have my y prime is minus y over x, is there a way to get rid of the y? Yeah.
Well, you said that y is 1 over x, so.
Y itself is 1 over x. In this situation, if I could solve for y, I could have done it, and I could get 1 over x, and put that in place of y. And then that would simplify to 1 over x squared. So the answers are, they're equivalent answers. Right? So this is a bona fide answer. Like, if you could figure out what the y is, it's going to coincide with what you expected it to be based on what we were doing before. So at this point, you're probably thinking, well, if what we did before worked, why are we doing it this way now? Like, well, are you just torturing us, Jhevon? Okay. The next example. The next example is going to start to show you why something like this, why is method 1 something that you'd actually want to consider. Here's another example. So, find y prime. So we're studying something, and this is a relationship that we figured out. Now, how would you find the derivative of y in that situation? Now, what we notice is, in this situation, it seems like implicit differentiation was totally like optional. Like, why would you even do it that way? You don't have to do it that way. Just solve for the y and then find the derivative. So just use what we've always been doing. So let's say you had that attitude when approaching this guy. Could we solve for y? Could we solve for y here? Do you see how to actually solve for y and kind of use what we did before? Get some black markers. Could we solve for y? It's totally confusing. I'll give you a hint. Because we can. The answer is yes.
The answer is yes.
Hint. That equation that I just wrote down is actually, if I just rearrange things a little bit, is actually that equation. Now, do you see how you can solve for y?
Quadratic.
It's a quadratic, right? A very fancy looking quadratic, but it's a quadratic nonetheless, right? This is like your A, this is like the B, and this is like the C. So this really looks like AY squared plus BY plus C equals. And we know how to solve that. There's a thing called the quadratic formula. So you could actually solve for y. And your y would be equal to minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And so now the question is, would you want to have to find the derivative of that? The answer is probably no. So yes, I could go along with this and just do what I did before. But would you really want to do that? Probably not, right? So let's approach the same problem. Again, the goal is to find y prime, but let's not do it this way. because solving for y is going to be just downright troublesome. So yes, we can do it, but we kind of wouldn't want to have to go that route. So now, how would I find y prime without the need to solve for y? Okay, go, based on what we know about implicit differentiation. We're just going to differentiate both sides. So, start with the first term. What would the derivative of this look like?
10x plus 2.
Well, there's a whole first term, right? There's this times y. What would the derivative of that look like? Every time you see a new situation, you think to yourself, what rule do I know would apply here?
The product
The
rule.
product rule,
So,
right? So this you think of as one function, that you think of as another function. So what derivative would look like?
5x squared plus 2 times 1. And then plus,
Well, you're leaving this one alone, the 5x squared,
yes,
and you want to differentiate the second function. What is the derivative of y?
y prime.
Y prime. Okay.
Plus
Plus
y,
y, you leave that one alone, and then
10x plus 2.
differentiate that. So you just use the product rule, and of course use the chain rule when you're differentiating the y. What about this part? Plus, now you want to find the derivative of this. And so now when you say, I want to find the derivative of that, you immediately think, what rule applies here? What rule applies here? Product rule again. That's one function times another function. So I'm going to differentiate that function, leave the other one, plus leave the first, differentiate the second. What is that going to look like here? F prime?
4x to the third.
4x to the third times the g, which is y squared, plus f, which is x to the fourth. What is g prime? What is y squared? Derivative of that?
Could it be 2y prime?
No,
Just 2y.
no. Yeah,
2y times y prime.
2y times y prime, because of the chain rule, right? When you see that y squared and you want to find the derivative of it, remember, you're thinking of it as the y is some inside function that you don't know. So you're going to apply the chain rule. To find the derivative, you differentiate the outside, leaving the inside alone, then you multiply by the derivative of the inside. So it's going to be a 2y y prime. Yeah.
So why didn't we also use the chain rule for the first y?
We did. So if I had the x of just y, I think of, hey, that's an inside function. Power rule says bring the 1 down, subtract 1 from the power, multiply by the derivative of the inside. But now I have y to the 0, which is just 1. So it just simplifies to y prime. Right. I'm always applying the chain rule. Whenever I see a y, I'm thinking chain rule to differentiate. But if you just have y by itself, it just drops down into y prime. Right? So yeah, if you think of the y, it's an inside function. I don't know what it is, but it's some f of x that I don't know about. So that means you apply the chain rule. Every time you differentiate a y function, multiply by y prime. Move on to the next side of the equation, derivative of this.
12x.
12x squared. I don't need an x prime because x prime is 1. It's d dx. So now I just get this equation, and what do I need to solve for? Well, I want to find y prime. Now my y prime is here. Now at this point, finding y prime is just a matter of algebra, right? How do you solve for this guy that you want to find? Well, you isolate them, right? So I'm going to keep everyone with a y prime on one side. 5x squared plus 2x times y prime, that's this guy, plus 2x to the fourth y times y prime, that's that guy. And then I'm going to move everyone else to that side. So here I have the 12x squared. I'm going to subtract this part. And then subtract that part. How do I solve for y prime now?
You can factor down the y.
Right, I can factor out the y prime. I'm gonna have that whole thing. 12x squared minus y times 2x plus 2 minus 4x y squared. And then I can find y prime. It's going to be this guy. Now, yes, this looks like a big mess, but I want you to imagine for a second what the answer would have looked like and what you would have to have gone through to have done it directly, right? Imagine this thing, right? Plugged in here, here, and here, and imagine how big and monstrous, that's what you would have had to do for this to do it directly, right? So implicit differentiation is important because there are times when you could avoid doing it, but you wouldn't want to. Here's another example, and this should probably kind of convince you once and for all why this is actually important. So this is a very important curve. It's called the folium of Descartes. Descartes, you know, the same guy as like, I think therefore I am, that guy. He was actually an amateur mathematician. And he's actually responsible for a lot of nice math formulas. In fact, the XY plane, you know the XY plane? That whole thing that we just take for granted? He came up with the XY plane. Like, you know what? I'm gonna draw a picture to represent this equation I'm looking at. No one ever did that before him, right? And it's like, it was like one of the turning points in mathematics, yeah. So that guy was studying this curve, right? Now let's say you wanted to find the derivative of this. And you might say, you know what? I'm not about the implicit differentiation life. That's not me, not into it. I want to solve for y and then find the derivative that way. You would be at a loss because there was another mathematician by the name of Galois who is kind of going to come and rain on your parade because Galois actually proves a theory that says it's actually impossible to solve for y in this situation. And I don't mean hard. I don't mean it's difficult. I mean it's literally impossible to have y equals with nothing but x's on the other side for this particular equation, right? In fact, he proved that once you have a polynomial where the power is 5 or higher, there is no general formula. So like the quadratic formula that you're used to, yeah, we have one for quadratics, we have one for cubics, we have one for 4th degree, but once you hit 5th degree, no such formula exists. Like it's a toss-up, whether you can solve for it or not, there's no general formula. So y to the 7th, once you see that, it's kind of like, now we're getting in shaky territory. We might be able to solve for y, but we might not. Turns out in this particular situation, you can't. Even if you wanted to, you cannot. It's impossible to solve for y here. So, if you're interested in taking derivatives, implicit differentiation is the only game in town. There is no other option. So it's not something like, take it or leave it. Yeah. I'll just forget about implicit differentiation and always do. No, you don't have that option. It's impossible to do it the old way here. We need implicit differentiation. Now, given that we know implicit differentiation at this point, let's see what would the derivative looks like. So we're just going to go differentiate both sides. Derivative of x squared, 2x. Derivative of y to the 7.
7y to the 6th times y prime.
That's right, she's got it. Yeah, she's got it. Derivative of 2y.
Times 2. Oh, no, there's no y.
Yeah, so what do you do?
Minus 2 times y prime
Yeah,
equals 0.
equals 0. Now y prime is just a guy that you can solve for. So using algebra, so you are going to isolate the y prime. subtract 2x from both sides, then you can factor out the y prime. Then you can just divide both sides by that thing. So it's minus 2x over 7y to the 6 minus 2. And that's your y prime. So you were in an impossible situation, but we were able to find a derivative. We're able to do calculus in this impossibly hard situation, right? And that's the power of implicit differentiation. Now, there are some valid concerns at this point. You're like, well, we can't know what y is, but y is in our answer. Is it even useful anymore? And it turns out that such an answer is still useful, and we'll talk next time about how it can be useful. Yes?
Are we having a quiz Wednesday because we don't have class Tuesday right now?
Yeah. So we'll just move this one. So Tuesday is like a Monday schedule, or is it like something?
Tuesdays and Mondays.
So, yes, don't show up for Tuesday. However, on Wednesday, yeah, so the quiz will go up to everything up to like basic implicit differentiation. So know all your derivative rules, so be able to state the power rule, the chain rule, all that good stuff. Know derivatives of special functions, like what is derivative of ln of something, what's derivative of e to something. And then just know how to calculate a bunch of derivatives, including implicit differentiation. Lots of derivatives on there.